Welcome to the chapter on glaciers. First, some cold facts about glaciers. Presently, about 10% of the land area of Earth is covered with glaciers, 15 million square kilometers. That's a lot. We don't think about it much because, well, we're not living where they are. And we'll be living where they were less because they are melting fairly quickly. Glaciers store about 75% of the world's fresh water. Most of the world's water is in the oceans, of course, but out of the fresh water, 3/4 of it is frozen. Out of the 25% that's not frozen, the vast majority of that is underground. This is just crazy when you think about how much this is. The Antarctic ice is in places over 4,200 meters thick. That is about 2.5 miles thick ice. Glaciers covered over 75,000 square kilometers of the US, with most of the glaciers located in Alaska. That was in the past tense. This has decreased significantly. And during the last ice age, glaciers covered 32% of the total land area of the Earth. Here's where glaciers are, or were. We have two major types. We have alpine or valley glaciers that occur in elevations, in mountains, and they're there because of the altitude and the colder temperatures of the altitude. We also have ice caps or continental glaciers that occur because they are further north or further south. This is what a lot of people think of when they think of a glacier. Little teeny patch of ice. That's about it. Now keep in mind, a glacier is not really just snow. This is the other thing that is a glacier. It's a weird photograph, but most of this is ice. In fact, the Ross Ice Shelf, and the Fitch-Norana Ice Shelf are ice out over the ocean. And it is from the Ross Ice Shelf that the biggest ice flow or iceberg ever created broke off a few years ago. I think it was B-15A or something like that it was named. It was big enough to land jets on. It was almost the size of some of the smaller states back east. Where do glaciers form? Well, pretend like you get some pancake batter and you stack it up, or you pour it out on your countertop. When you pour it out, the glacier is going to flow out from the direction where your pancake batter is poured. It's the same thing with real glaciers. If you have an area where snow accumulates faster than it melts, the snow will change eventually to ice and will flow out in all directions. This is a continental type glacier. Here's an example of a valley or alpine glacier. The snow compresses to firn, also known as neve, F-I-R-N or N-E-V-E. That ice then undergoes an elastic flow where it distorts and reconfigures, scrapes the bottom of this valley. Now, a couple of terms. This is the zone of accumulation, where you're building up the glacier. Down here is the zone of ablation, where the glacier is being either evaporated, and yes, ice can go straight to a gas. You've seen this in your freezer before. And where it also melts. If the glacier is melting faster than it's flowing downhill, the front of the glacier will move backwards. Now keep in mind, that happens even though the glacier is still moving downhill. It's just that the melting occurs faster than the moving downhill. If there's more snow accumulating and changing to ice than the melting can take care of, the front of the glacier, the terminus it's called, T-E-R-M-I-N-U-S, will advance. Now, glaciers move back and forth according to the season. Not a big deal. In summer, the terminus will recede or move up the valley. Or, in the case here, will move up across the continent. In the winter, the glacier will move out from the zone of accumulation or down from the zone of accumulation. This is kind of cool. You can have glaciers anywhere on the planet depending on the elevation or altitude. If you're at 0 degrees north, which you should know is the equator, all you have to be is a little over 5,000 meters in altitude and you can have a glacier because you'll have enough accumulation so that it won't melt. This, by the way, has to be changed a little bit. This line has to be raised slightly because temperatures are rising. I'll show you pictures of Kilimanjaro in just a minute to show you this. At the North Pole, the snow line which is the line above which there is permanent snow and it never melts, is all the way to sea level. Do we have a snow line in Arizona? Well, let's say Flagstaff is somewhere right around here. We don't quite have a snow line. Even the San Francisco peaks, where we'll have snow into June, sometimes July, completely have their snow melt. Colorado, on the other hand, with some of their 14,000-foot mountains, does have a snow line, and there are places where the snow never goes away, and they're little mini snow packs. I don't know if I'd still call them glaciers. Heck, even Glacier National Park is now, well, it should be known as National Park because most of the glaciers are gone. Here's Kilimanjaro, 1912, 1953, 1976, 1989, and the 2000. The outside light blue is where the glaciers used to be in 1912. The white is where the glaciers are in the year 2000. In the year 2010, this is even much smaller. This is important because the people down from this in, I believe it's Kenya, rely on the melting water. Once there is no longer melting water year-round from this, they're going to be in trouble. Okay, how glaciers move. There's basal slip and plastic flow. First, you've got to get this idea. The snowflakes aren't what make the glacier. They're what form the glacier. These snowflakes compress into granular snow, graupel, it's called, G-R-A-U-P-E-L or L-E. Then that changes to firn, which is granular ice crystals, and then you end up with glacier ice. This is what that glacier ice looks like under polarized light. This is a very cold laboratory, by the way. You wouldn't want to be working in here in your normal clothing. This is a slice of a glacier, and those are the little firn or glacier ice crystals. These distort under huge amounts of pressure and cause the glacier to flow. Here's what happens in a valley glacier. First, let's identify some terms. There's what the mountain used to look like. The glacier eats out at this mountain. This is called the head wall. Here's the bergschrund, the place where the berg or the ice starts. Again, here's the zone of accumulation, the zone of ablation. A little place that's dug out is called a cirque. That's French for arena, and you can imagine the French going up there in the summertime and having, well, maybe a circus up there. It's related to the same word. Then here are rock steps where the ice goes over, and because the ice flows faster over the rock steps, it cracks and creates what are called crevasses. And here's the terminus. Any rocks that get carried down by the glacier, either on the bottom or that have fallen on the top, and they get dropped off as the glacier moves down and it gets melted back, create a pile of debris, and that's called a moraine. We'll cover that in just a while too, so don't worry. The glaciers often will have, especially lately, have running water down here, and they will allow what's called basal slip to occur. The glacier actually slides. Now when it slides, I don't want you to think it's like you going across a slip and slide. This is hundreds of thousands of tons of ice, and in the base of it are rocks, and these rocks will scrape the bottom of this thing. Imagine you laying down here, but with a ski coat on so you wouldn't freeze, and a mile of ice across you, on top of you, and in the bottom of the ice there are these boulders, and this whole thing is scraping across you. It'd be hard on your face. Oh, bad to think about. Here, by the way, is a glacial ridge called an arête. We'll talk about that in a while. Here's what happens inside the glacier. Everything doesn't move at the same speed. The top is called the brittle zone because it hasn't been compressed into the firn or the granules yet. Near the bottom, it moves slower. As you get toward the brittle zone, it moves faster. This is called plastic flow. Excuse me. It's not the same as the basal slip where the glacier just slips across here. And again, this is showing that rocks can get plucked out of the bed of the glacial valley. Water seeps into here. It can refreeze and crack the rock because water expands about 11% when it freezes. Here are crevasses forming on the outside of the curve. Usually these are no more than 50 feet deep. People have fallen into these and they haven't come out. So next time you're out walking on a glacier, be careful. When the ice goes over a rock step, because the ice will move faster, crevasses form too. This is kind of cool. Scientists have drilled down into glaciers, put pipes down in here. What they find out is that the center of the glacier, away from the edge where there's less friction, moves faster. Also, again, places away from the very bottom move faster because there's no friction, or at least there's reduced friction, I should say. So if you put all these markers on top where the pipes were, the marker in the middle tends to move the fastest. Here's a typical crevasse. Here are typical people walking next to a crevasse. I think they're kind of crazy. One of the problems that can happen is this can be covered over by snow, and you won't even see the crevasse. You go traipsing across here and whoa! Good luck getting you out. If nobody's with you, it's going to be a chilly death. Here are crevasses as a large glacier moves down a valley. Now, I know this looks really flat, but you've got to understand what's going on under here. This ice is eating away at a valley underneath here. This guy is watching it happen. Now, glaciers can move from a few inches per day to a few meters per day. There are extremes on either side, but that's a rough estimate. I thought I'd throw those in again. Okay, oh, I know why I threw this in. Take a look. When the ice gets down to the ocean, if it gets to the ocean, pieces will drop off in a process called calving. I know it looks like calving, but it's called calving. And they form bergs. This is a fake picture that floats around the internet. It's not real, which is why I just called it fake. However, there is something important here. About 89% of the glacier is underneath the water. Only a little bit of it is on top of the water. Some of you know this is important because of a little boat that had a bad time a few years ago called the Titanic. Actually, it's happened to a lot of boats, just that that one was made into a big movie. You can sail by here in your boat and think you're safe, not knowing that a big portion of this is just waiting for your hole under the water. This is what happened to a Canadian boat. It hit something a little bit hard. I don't know where the break in it is. That may be the break. It got seized up in the sea ice. The sea ice froze around it, and it sunk a little while later. Apparently, this is being taken from the rescue helicopter. There's where the people were getting off of the boat. And here is a satellite picture of a valley glacier calving icebergs into, looks like a moraine-dammed lake, a lake formed by the dirt dropped off by the glacier during the melting season. Here's a typical shot of northern hemisphere icebergs. And again, there's a lot of stuff under here. You are seeing only the top of it. This is a typical iceberg from the south hemisphere or southern hemisphere. Because you have those huge ice shelves, these things can be equally huge. Again, we've landed jets on these things. They are that big. And little by little, they're melting away. This is another cool thing. Glaciers that have been there a long time collect things on them. Not just rocks from the mountains that they're eroding, but anytime meteorites or micrometeorites fall on them, these things get carried down and deposited either on the sides or the moraines. So great places to look for meteorites are the moraines of Antarctic glaciers. Let's pause there and pick up the rest of this a little bit later.